So 2 of these are soluble, 2 of these are insoluble. Which ones are which? All right, so the concept that we're looking at here is polarity. That is, like dissolves like. So with water, we know water to be a polar substance. What we need to pick out are the other substances that are polar. And so if I look at hydrogen fluoride, I'm going to see a molecule that is made up of 1 bond. That 1 bond is certainly polar. So we would expect, okay, if this is polar and water is polar, like dissolves like, HF is going to be soluble in water. Now, in the case of nitrogen, here I've got, again, a molecule of 1 kind of bond, a triple bond between 2 atoms of the same kind. So it's kind of the exact opposite. I've got a molecule that is made of a single bond, and that bond happens to be nonpolar. So the molecule is nonpolar. Since it's nonpolar, we would expect it to be insoluble in water. For the carbon tetrachloride, well, we're going away from single atom structures. But I can see here that I've got a molecule that has a steric number of 4, and all 4 of those bonds are identical. That's the very definition of symmetry. So this substance is nonpolar as well, which means it also is going to be insoluble in water. Ammonia, also has a steric number of 4. On its surface, you go, okay, well, all 3 of those bonds are the same. It's symmetrical, right? Well, we have to consider the asymmetry associated with that lone pair there. That's going to create the unbalanced distribution, and that's going to make it polar. So the top and the bottom were soluble, the 2 in the middle were not. And it looks like most of us are on the right track there. So good. Any questions about that before we move on? Okay, then. So the last concept out of chapter 6 is that of phase diagrams. Now, phase diagrams are basically graphs. And they are graphs that show 2 axes. Pressure on the vertical and temperature on the horizontal. Now, what are we graphing on this graph? We are graphing the phase of matter that exists at these particular temperature and pressure conditions. So what we are ultimately going to be doing is we're going to be looking at where is the substance a solid? Where is the substance a liquid? And where is the substance a gas? Now, the positions of the solid, liquid, and gas relative to their temperature and pressure have everything to do with intermolecular forces. One generally good rule of thumb is that the stronger the intermolecular forces are, the bigger your liquid and solid regions are going to be. Because liquids especially are basically governed by intermolecular force. The stronger the intermolecular forces are, as you saw in the post-lecture over the past couple of days, the more likely it's going to stay liquid, the less likely it is to evaporate. But that also translates to the solid as well. The stronger the intermolecular forces are as the solid, the higher the melting point is going to be as well. So for substances that have good, strong intermolecular forces, we are going to find larger solid and liquid regions. For the ones whose intermolecular forces are kind of weaker, we're going to see larger gas regions. And it's going to be difficult to see sometimes because a phase diagram generally will try to show all three. What we have to look at is the scale of the diagram. And in particular, what temperature and pressure conditions we're really talking about there. But before we get into that, we got to get into a little bit of vocabulary. Because there are some things other than solid, liquid, and gas on that phase diagram. There is, for example, something called the triple point. Now, if we go back to this diagram that I drew, the triple point would be represented by this spot right here. It is the interface between the solid, the liquid, and the gas phase. At that particular set of conditions, you will find solid, liquid, and gas all together at the same time. And not only are they all together at the same time, they're all at equilibrium with each other. Meaning, all 6 of the phase changes are also all happening all at the same time. You have liquid turning into gas. You have gas turning into solid. You have solid turning into liquid. All of the known phase changes are all happening at the same time at the triple point because not only are all 3 phases present, they're all in equilibrium with each other, meaning they're all in this constant state of conversion. So that's the triple point. The critical point is a very specific temperature and pressure condition where we could no longer tell liquid and gas apart from each other. So again, going back to this diagram here, this spot right there, that would be the critical point. At temperatures and pressures above that critical point, we no longer will see liquid and gas. What we will see instead in this zone here is something called a supercritical fluid, SCF. And so that is the name that we give to that phase that is kind of this indistinguishable mix of liquid and gas. Most common example of this is carbon dioxide. Supercritical carbon dioxide has a number of different uses, but what's probably its most common use is in the use for as a solvent. Think dry cleaning. There are certain clothes that you cannot put through your washing machine. either because they will be damaged by the washing machine or the chemicals that are in the detergent will start to attack the finer fabrics. So you send them to a dry cleaner. And a dry cleaner uses a series of volatile organic chemicals that, because they are in the same polarity as grease and sweat and body oils and that other kind of stuff that makes your clothes stink, it gets the clothes clean. And because they're volatile, they go away. But the problem with all of those VOCs is that they're flammable also, which is why a lot of dry cleaner fires exist. Supercritical carbon dioxide does the same kind of thing. It's a non-polar solvent. So it would react and it would dissolve oil, grease, other kinds of stuff that comes out of your body as you dirty your clothes. But carbon dioxide is inflammable. And so it's considered a greener alternative, although carbon dioxide gets a bad rap for being a greenhouse gas as well. And look at the phase diagram of carbon dioxide. Another reason for its use, supercriticality does not require extremely high temperatures or extremely high pressures to achieve. And so it's kind of attainable. So let's take a look at a phase diagram. This is the phase diagram of carbon dioxide. And you can see, as to my earlier point, the temperature for supercritical is somewhere right around 30 Celsius. So if you can get the temperature above 30 Celsius, which is like just barely above a hot summer day, you can get supercritical carbon dioxide. You just need to have the pressure up around 100 atmospheres. That part's a little bit more difficult, but in a normal kind of like compressed air tank, it's not that unreasonable. So again, interpreting this as a graph, what we can see, and it'll always be this way. Solid will always be the top left portion. Gas will always be the bottom right. Liquid will always be in the middle of the two. So you can always count on that in a phase diagram. Anywhere along these bolded lines represents a phase change. Now, of particular importance to us usually are the phase changes that occur on this line right here. That line right there, 1 atmosphere, that's important to us because that is what we would consider normal conditions. Because that's atmospheric pressure. So when you are asked for a normal boiling point or a normal freezing point, you want to look for that condition, that phase change on that 1 atmosphere line. Now, if it asks you just for any set of conditions like this middle bullet point does, we can pick anywhere on that bolded line. But if it asks us for normal conditions, we need to give them normal conditions. We need to give them that 1 atmosphere. So interpretation of phase diagrams is really not that difficult. It's just graphical analysis. What is the expected phase of matter at 10 atmospheres and -80? Well, I can look at it and say it's probably a solid. If I wanted to draw that out though, I just need to draw some crosshairs here. Okay, 10 atmospheres is about there, -80 is about there, they cross over here, that's the solid region. Name one set of conditions where carbon dioxide will freeze or melt. Well, again, I could choose anywhere on this blue bold line here, because that blue bold line represents the phase change between liquid and solid, which would be either freezing if I was going toward solid, or melting if I was going toward liquid. So I just need to pick a set of conditions. What ones I pick really don't matter that much. For ease, I already drew a line on the 10 atmospheres. I'm gonna just draw a line down here. 10 atmospheres, and well, it looks pretty close to the same. We're just gonna bump that negative 55 degrees Celsius maybe. Scale's not very good here, so be pretty generous with the estimation. Why do we not see liquid carbon dioxide when we use dry ice? Well, if I look at that 1 atmosphere line, the one I made here in blue originally, I can see that liquid carbon dioxide doesn't exist at 1 atmosphere. Doesn't exist at all. So why don't I ever see any liquid when we use dry ice, at least liquid carbon dioxide? It's because it doesn't exist at this condition. Liquid's not present at 1 atmosphere. To get to the liquid phase, I've got to go up to somewhere around 5 atmospheres. Actually, a little bit above. So that's phase diagrams. It's really, it's not that complicated of an idea. It's a graphical analysis thing more than anything. And the kinds of questions that you're going to get on it are largely going to be questions like this. Can you interpret the graph? Do you know the different zones in that phase diagram? Can you point to a triple point? Can you point to where the solid is? That kind of thing. All right, so let's try one ourselves here. I've got 3 questions for you. What is the phase of water at these 2 different conditions? And then this last is also fill in the blank. How many phases of matter are present when water is at the freezing point? So look at that phase diagram and answer those 3 questions. All right, let's look and see how we did. So for the first question, what is the phase of matter or the phase of water at pressure equals 0.01 and temperature equals 200? So if I draw those, 0.01 and 200, we are talking about something that is gas phase. Second question was the phase of water at 10 atmospheres and 100. So same thing, 10 atmospheres, 100 Celsius. We're talking about a liquid there. And then the question at the end, how many phases of matter are there at the boiling point? Freezing point. Well, that would be 2. Because at the freezing point, at any phase change, there would be two phases of matter present. There would be the phase that you are transitioning from and the phase that you're transitioning to. So as the water is freezing, there's going to be liquid present and there's going to be solid present. Both. When the water is frozen and no longer at the freezing point, then there would just be the one phase. But while the process is being undertaken, we have to assume that if we are at one of those conditions, we're at equilibrium. Both are present there at the same time.